We don't really have
Okay, so today we actually are going to finish up with some material. Your practice exam for your exam on Monday is up. I'll open up a block of office hours Monday morning in case you have any remaining questions about that after you go through it for the weekend. The stuff we do today will be quite lightly covered on that exam. Again, look at the practice exam for the idea of levels of like depth of those questions, but shouldn't be too bad, won't be a big emphasis. I just want to make sure that we have time in our next couple of minutes. So that's why we're going to go over some of these concepts today. So we're going to finish thinking about how our gases dissolve into the blood, a little bit about how they're moving through the circulatory system. And then we're going to jump to the end of that regulation packet because there's one concept that's closely related to this diffusion of gases idea that doesn't require us to have any knowledge of what's going on with the hemoglobin and the complexities of that. So I'll do that portion during our next unit. Okay, but you'll follow along. Okay, so when we left off, we were talking about the solubility of gases in liquids because we know that we have partial pressures, this new idea of partial pressures of gases in the air around us. We can add together the pressures of any given gas, our nitrogen, our oxygen, a tiny bit of carbon dioxide to get our total pressure in any given system. Okay, so for example, in the atmosphere, and those are just basically percentages. But when we think about liquids, we have a slightly different situation because we now need to think about how soluble that gas is in a liquid, so how easily it's going to dissolve. We're not going to have to do these calculations, but what we want to know is that if we have a partial pressure of a gas in air, our gas is going to follow our general basic chemistry properties, physics properties. I don't know exactly what this is. It's going to reach equilibrium, right? We've talked about equilibrium here in this class some. I hope you have talked about it in other classes. So what I'm telling you now is that despite the fact that there are differences in solubility between different gases, if you have a partial pressure of oxygen of 100 in the air, it's going to dissolve into the liquid and it's going to reach equilibrium in that liquid. So it's going to dissolve however much it can until you also have a partial pressure of oxygen of 100 in that fluid. Okay, so that's the takeaway here. So gas in the air is reaching equilibrium with gas in the fluid. Okay. The bit about solubility is that if we compare oxygen to carbon dioxide, right, our partial pressure of oxygen in the air, the 100, and the partial pressure of oxygen in the water at 100 looks like this. But because oxygen and carbon dioxide have different solubilities, those same numbers mean slightly different like concentrations of the gases when we're thinking about fluid, because carbon dioxide is more soluble in water. So if we had water where the partial pressure of carbon dioxide was 100 and the partial pressure of oxygen was also 100 in that same fluid, there would be like more molecules of carbon dioxide in it. And that's all that solubility piece means. But in the situation, we also see that carbon dioxide is coming to equilibrium with that partial pressure with carbon dioxide in the water. We care about that because this little column is essentially supposed to represent what's happening in our alveoli in the lungs, where we have the air. So that's the gas part. And the capillaries lying right next to them. So that blood plasma is mainly water. So what this is showing us is that the partial pressure of gases in an alveolus is going to reach equilibrium with the partial pressures of those gases in your blood in the cardiovascular system. And this is why. Okay, So we're going to move on to that second objective. That's where we officially left off last time. And we're actually going to look at the alveoli in the blood. Okay. So when we're thinking about exchanging oxygen and carbon dioxide, we're thinking about the fact that those two gases, the oxygen and the carbon dioxide, have to move between the lungs and the blood at the level of the lungs. They're going to move around in your bloodstream, and then you're going to have the oxygen and carbon dioxide crossing cell walls again, cell membranes again, at the respiring tissue. So like at your cells out in your body that are doing metabolism, that are actually doing stuff, okay? So these two things are going to determine how much oxygen and carbon dioxide there is in your blood, okay? And in order to understand what's going on, we also want to think about, okay, how much oxygen and carbon dioxide do we have in the air in the alveoli in the first place? Okay, so that's this alveolar PO2 and PCO2. Okay. So when we're thinking about gas exchange, we're again going to be thinking about gradients. In this class, we have tons and tons of gradients, right? We have chemical gradients, we have pressure gradients, we have electrical gradients, right? So now we're thinking about a new type of pressure gradient, kind of. This is just a partial pressure gradient. It's going to work exactly the same way all our other gradients did. So we're going to have our gases diffusing down their partial pressure gradients. So these gases are still just trying to reach equilibrium. They're trying to be nice and evenly spread out, nice even pressure everywhere. So they're going to move from wherever there's high pressure to wherever there's low pressure, okay? So overall, when we saw movement through our lungs, we saw that that pressure difference between your atmosphere and your alveoli was driving the ventilation, the movement of air. When we're thinking about these partial pressures of gases in the alveoli and partial pressures of gases in the blood, same thing's happening. So a gas, say oxygen, is going to move from where we have a high partial pressure to where we have a low partial pressure. So we're still just going from high to low. Okay. Now, if you're tracking oxygen, ignore carbon dioxide. If you're tracking carbon dioxide, ignore oxygen, because these gases are each traveling down their own partial pressure gradients. So when we were thinking about the atmosphere and its total pressure, right, we had to add together all these gases. We do not have to do that if we're thinking about these partial pressure gradients. So compare oxygen to oxygen, carbon dioxide to carbon dioxide. Okay. So we had a diagram like this right at the top kind of this unit. But what we're thinking about here, right? So we have air coming in from the atmosphere here up top. So these two gases have partial pressures in the air, okay? So out in the atmosphere, there's a partial pressure for oxygen of 160. And we have very, very little carbon dioxide in the air in the atmosphere. Only a partial pressure of 0.3. But as we breathe that air in, as we move the air into our alveoli, it's mixing in with that dead air. We talked about the difference between our minute ventilation and our alveolar ventilation before. So we know that we had some dead air kind of stuck down in the lungs that mixes with fresh air every time you breathe in. So we're going to see changes to those partial pressure because of that mixing. We're also humidifying the air, so we're adding some water vapor. So we're making some changes to these partial pressures in that process, okay? So do not worry about remembering atmospheric partial pressures, but in the future, you will want to know some things about our partial pressures in the alveoli, because these are relevant to the partial pressures in the blood, okay? So once you're in the alveoli, a typical partial pressure for oxygen is 100, okay? So oxygen 100, hopefully that's an easy number to remember, okay? A 0, you got lots of zeros here, right? Almost. Okay. And the partial pressure of carbon dioxide in that alveolar air is going to be at 40. So that mixing with the dead air especially made a huge difference, right, to that partial pressure of carbon dioxide in the atmosphere versus in the alveolar air, right? We see a big difference there between those two, okay? So that's why we want to remember that that happens. Okay, so once we're in the alveoli, we have this air in the alveoli with these partial pressures. the next thing that happens, right, is the partial pressures of those gases in the alveoli reaches equilibrium with the blood, okay? So that means that the blood coming out of the lungs, going to the heart, and then coming out of the heart, right? All of that blood is just going to have those same values as the alveolar air, right? That's what equilibrium means. We made them equal, okay? So in our pulmonary veins here, we see those same partial pressures, 100 for oxygen, 40 for carbon dioxide, okay? We go through the left side of the heart, right? Nothing changed, right? We're not doing any gas exchange here. So out in our systemic arteries, so the blood that your heart is pumping to your body, we're still just the same, okay? So we see those same partial pressures, 100 for oxygen and 40 for carbon dioxide, until we get wherever we're going, right? Until we get to the capillaries, feeding the cells, feeding the tissue that we're traveling to, we don't see any changes for those partial pressures. Everything's just the same as that alveolar air, okay? When we do see a change is as we pass that tissue, right? So these cells out in, I don't know, let's say they're liver cells, whatever, right? So they're making ATP, they're doing cellular respiration. That's a form of internal respiration, right? Respiration having to do with gas exchange. So they're breaking down glucose. They need oxygen for that. So they're pulling in oxygen and they're producing carbon dioxide as a byproduct of breaking down that glucose molecule, right? So they're giving off carbon dioxide. Okay, so here is where we are going to see a change to our partial pressures. So in the cells, these cells, they're actually going to have a lower partial pressure of oxygen than our arteries did. This is what allows them to pull in that oxygen, because oxygen will go from this high partial pressure in the arteries to that lower partial pressure in the tissues, so high to low. Okay. And they're going to have a higher partial pressure for that carbon dioxide. So that partial pressure of carbon dioxide in the cells, usually about 46. All right. So this is going to allow them to push carbon dioxide into the blood essentially. So high to low, 46 towards that 40. Okay. So as our blood is practically in contact with these cells, this tissue, as it's going through the capillaries, we have this nice slow flow of blood past. We have time for them to reach equilibrium, okay? So systemic arteries coming in at a partial pressure of oxygen of 100, partial pressure of carbon dioxide of 40. Our cells had a lower oxygen, higher carbon dioxide. We then have our blood reaching equilibrium with those values, okay? So until you get to tissue, you have a partial pressure of oxygen of 100 in the blood. Once you get to the tissue, you match that partial pressure of 40. So as we pass those cells, pass that partial pressure of oxygen of 40, because they're using that oxygen, so they have that lower amount of oxygen, pulling oxygen in to that tissue until it reaches equilibrium. So then the blood returning to the heart, you've taken oxygen out until you matched that 40 value. So partial pressure of oxygen in your systemic veins is 40. Carbon dioxide, same idea, just reverse direction, right? So we had a higher partial pressure of carbon dioxide in those cells. So it was 40 in your alveoli and the arteries, 46 in the tissue, which lets it push that extra carbon dioxide into the blood. So we match that 46 value. And now we have a partial pressure of carbon dioxide of 46 in the systemic veins. So this is really just the two places we see changes to those partial pressures, right? So as we match the alveolar air is where we get our first value for our pulmonary veins at systemic arteries. And then we match the tissue as we pass tissue in our capillaries. And then we see that change there. So that value carries all the way through to the right side of our heart, in through the right atrium, right ventricle, pulmonary arteries, and out to the lungs, okay? So that's our value for the partial pressures of oxygen and carbon dioxide in those arteries going to the lungs. which are then going to participate in gas exchange and come to match that alveolar air. So to do that, we're taking that excess carbon dioxide and pushing it into the alveolar air, right? So that's why we have the CO2 coming out, okay? So 46 was higher than 40, so carbon dioxide comes out. Oxygen is at 40, alveolar air is at 100, so oxygen is coming in, bringing us back to those original values. Okay. So that's something called the oxygen cascade, is this sort of exchange, especially of oxygen as we're moving through our cardiovascular system and passing the lungs and the tissue. Okay, so the diffusion is happening really quickly. So the alveoli and the blood just have that really thin barrier between them, right? We got the type 1 alveolar cells, a basement membrane, and an endothelial cell in the lining of the capillary, okay? And we got a large surface area because we have that bubble shape to the alveoli, which extends how much room we have basically for this exchange process to happen. We also have tons and tons of capillaries covering over the lungs, okay? So it happens to be the case that in about a third of the length of the capillary, you already match those values. You have that alveolar air reaching equilibrium with the blood really quickly. Okay, so this is showing us the length of the capillary. So this would be like 100% of the length, the total length. So about a third of the way through the capillary, you get to that alveolar partial pressure of oxygen in the blood. Okay, so this is showing us the partial pressure of oxygen in the blood. So in the veins coming in, the partial pressure of oxygen is at 40. We're going through the tissue of the lungs, essentially coming into contact with that alveolar air that has a partial pressure of 100. And we reach equilibrium a third of the way down the capillary. That's all this graph is showing. Same thing is happening on the carbon dioxide side, okay? So the venous blood coming into the lungs is at a partial pressure of 46, but the air in the alveoli has a partial pressure of 40, okay? So about a third of the way through the capillary again, you come to equilibrium with that alveolar partial pressure, okay? So it doesn't take long for this gas exchange to happen in the lungs. So the gases are just diffusing down their partial pressure gradients. And this is basically just writing out for you in words what I was pointing out as I was running through that picture. So this is telling you that we've just covered that we reach equilibrium in the lungs. Those two graphs were showing you the values and how fast that happens. So this is now talking about what's happening at that tissue level. So our tissue cells have a low partial pressure of oxygen, 40 or even less, okay? The blood coming into them in the arteries has that 100 millimeter of mercury partial pressure, okay? So the oxygen moves from the blood to the cells down that partial pressure gradient and comes to match, giving us a partial pressure of oxygen in the veins of 40 millimeters of mercury, okay? So when we're tracking the carbon dioxide, right, the carbon dioxide in the cells is building up because those cells are respiring. They're producing their carbon dioxide as a byproduct. So you have a partial pressure of about 46. The arteries coming to the tissue had a lower pressure, partial pressure of 40. Okay, so this means that we're going to go from 46 to the lower number 40. So carbon dioxide is moving from the cells into the blood. Okay, so it's diffusing from the cells into the blood because of that gradient. And the veins are essentially coming to equilibrium with those cells. So the systemic veins have a partial pressure of 46. Okay. So this is all just about reaching equilibrium at two places, the level of the alveoli and the capillaries in the lungs, and then at the level of the capillaries in the tissue. Okay. Okay. So when we think about that tissue, right, it is the case that this is a kind of generalization. The exact amount of oxygen and carbon dioxide being used and produced is going to be dependent upon how active that tissue is, how much you're using that organ system, how much ATP it needs, right? So how much work it's doing. So if there's greater metabolism happening at the level of the tissue, there should be greater exchange of gases, right? So if you're way below 40 for your oxygen in the tissue, right, you're just going to get more oxygen from the blood, essentially. So these should be playing off each other like that, basically. So if there's a greater rate of metabolism, there should be a greater exchange of gas. Okay. So this means that while we're using these numbers as our ballpark typical values, our partial pressure of oxygen and carbon dioxide in any given vein out in our body, right, out in our system might vary, right? If your legs are using a different amount of oxygen, producing a different amount of carbon dioxide because you're out on a run or something, then your femoral vein might have a different partial pressure than your portal vein to your liver or something like that. That's what that note about the variation between systemic veins means. So that is why it's always labeling this as mixed venous blood, right? So this is telling you that it's kind of an average as that blood is coming back to the heart, right? Okay. So that's just a little bit of an explanation about like what we're labeling there. Okay. So the factors that are going to influence this, right, are going to be how much oxygen and carbon dioxide we actually have in the air we're breathing in. Right? We've given very typical values at sea level, average normal amounts of carbon dioxide, oxygen, nitrogen in the atmospheric air. But you could be in a situation where for some reason you're in a room that has like almost no oxygen, or you're on a ventilator, someone's giving you supplemental oxygen, right? These values can change. And if you change the values of the partial pressure of oxygen or carbon dioxide in the air you're breathing in, that would also change these partial pressures in the alveoli, okay? Bigger factor in your day-to-day life is going to be essentially how fast you're breathing. So we talked about minute ventilation as being basically the amount of air you're breathing in per minute, right? It was dependent partially on the respiration rate. So that is really going to be the main way that we're going to change those alveolar partial pressures in practice. We can breathe faster or we can breathe slower, okay? And then the rate at which you're using that oxygen and producing carbon dioxide makes a difference on the tissue end, okay? So the most critical thing here is going to be matching how fast you're breathing, essentially matching the rate of alveolar ventilation to how much oxygen and carbon dioxide you're using and producing. So if you're using a lot of oxygen, you're going to want to breathe more quickly so that you get more oxygen, essentially. Okay. All right. So we have some terms that we use to refer to different, basically amounts of breathing relative to how much oxygen you're using and carbon dioxide you're producing. Okay. So this word hyperpnea, this does refer to faster breathing, so increased ventilation, faster breathing, but specifically, it's due to an increase in demand. So even though it has this word hyper in it, right? Hyper meaning more. This is actually a good thing. If you're using a lot of oxygen and producing a lot of carbon dioxide, you're going to want to breathe faster to breathe in more oxygen, breathe off more carbon dioxide. So hyperpnea is a word you would use to refer to someone who is breathing faster than normal, but it's specifically so that they can match demand, okay? So in hyperpnea, you're not going to see big changes in the partial pressure of oxygen and carbon dioxide in your arteries, so in that blood, because we've appropriately matched the demand, okay? Hypoventilation and hyperventilation are problems, okay? So hopefully, looking at these words, you can kind of predict what they're going to mean, right? So in hypoventilation, what we're saying is that we have too little ventilation. We're not having enough air. We're not breathing in enough air, hypoventilation, in order to meet the demands of our body. Okay. So if we think about that, right, we're saying we're not breathing enough air. Okay. So what does that mean? That means we don't have enough oxygen to do our cellular respiration to appropriately feed into the metabolism. Okay. So this means we're going to see low values for oxygen because we're using it up faster than we're breathing it in because we're breathing too slow or too lightly. So you'll see that your arterial partial pressure of oxygen is decreasing. So it's going down because you're not breathing enough. And that carbon dioxide is building up because ventilation does two things. It brings oxygen to your body, but it also lets you get rid of carbon dioxide, which is a waste product, and actually a waste product that's kind of dangerous for your body. So you're going to see that carbon dioxide is building up in the blood if you're not breathing enough, right? So you're not breathing off that carbon dioxide, so it's sticking around in your arteries, okay? So you'd see an increase in that carbon dioxide, okay? And hyperventilation, okay? This means that you're breathing too fast, right? So if you're hyperventilating, right, you've probably used that word in your normal life, right? But what it technically means, hyper, too much, too fast, a lot. Ventilation refers to that moving of air in and out of your lungs. So you're moving air in and out of your lungs too fast, okay? This means you're keeping that partial pressure of oxygen really high, right? And you're not actually using it at the tissue level, okay? So what you're going to see is a really high partial pressure of oxygen as you're bringing lots of oxygen into the body and then not using it, okay? And you're going to see that partial pressure of carbon dioxide dropping as you're breathing off lots of carbon dioxide without actually producing more. Okay. So you're going to see opposite changes in hypoventilation and hyperventilation in terms of those partial pressure values. Okay. Right. And here's a table of all sorts of words referring to issues with respiration and breathing. Don't memorize these, but they're interesting. So if you have extra brain space, go ahead and take a look. Okay. So we're going to talk about this one piece from the regulation of ventilation side. Okay. So thus far, we know that there are appropriate levels, appropriate partial pressures of oxygen and carbon dioxide in the blood. Right? That's what we were just talking about. Right? Now we're thinking about the fact that we're going to want to be able to sense those amounts of oxygen and carbon dioxide and potentially adjust some things in response. Okay. So we can control and detect those levels of oxygen and carbon dioxide to some extent. So a chemoreceptor, chemo for like chemical. So chemoreceptors sense a chemical. Okay. So a chemoreceptor is going to be able to detect those levels of oxygen and carbon dioxide. Yeah, it's at the end of that regulation bucket. So, and again, we're just thinking about this on a high, broad level. Okay. So there are going to be two places that we see these receptors. You're going to have one like in your central nervous system. So your central chemoreceptors are in the medulla oblongata. And you're also going to have receptors outside of your central nervous system. So specifically, you're also going to have these chemoreceptors in the carotid sinus, in the carotid bodies, which is where you see the split of your internal and external carotid arteries as they're going up your neck. Okay, so those are peripheral chemoreceptors. So two spots we can see them. All right. So those peripheral chemoreceptors are located in those carotid bodies. All right. They do project up to your brain. Okay. Don't worry about the specifics of that. Right. So what we want to know is just that those peripheral receptors can sense changes in carbon dioxide, and that's the main thing that they're responding to, they're only going to respond to changes in oxygen if they're really extreme. So actually, from your body's perspective, the most dangerous kind of thing is a dramatic change in carbon dioxide, really, rather than a mild change in oxygen. Okay, so the buildup of carbon dioxide, which is that waste product of metabolism, actually really influences the pH of your blood. And we'll talk about that in our next unit, how that works. But your body is going to respond with more alarm bells, essentially, if you start to hold too much carbon dioxide in your blood, you're not breathing it out fast enough, than if you have some changes to the oxygen level. Okay. So that's kind of the level to which we want to understand this. Okay. We're going to respond to those changes in carbon dioxide quickly, only really drastic changes in oxygen. So this is referring to how much air you're breathing, a minute ventilation, relative to the partial pressure of oxygen in the arteries. So the normal level that we just talked about for oxygen is 100, right? So oxygen should be at 100 in your arteries, okay? So what this is saying is that if your partial pressure of oxygen is dropping, say it drops to 90, you don't really change your minute ventilation, which means you're not really changing your breathing. At 80, you're still not really changing much. It takes until you get down to almost like 60 before you start to see a real change in how much air you're breathing in, right? So essentially what this is kind of implying is that you're not really going to speed up your breathing in response to changes in oxygen unless it gets to just like 60% of its normal value, right? So it takes a pretty dramatic change in oxygen levels for those chemoreceptors to respond. Now, this looks really different than the situation if we look at carbon dioxide levels. So if we look at carbon dioxide levels in your arteries, they should be at a partial pressure of 40, right? You can see that as soon as they're at 50, right, you have increased your minute ventilation, right? You are increasing that breathing throughout this curve, right? You don't have to like slowly wait until it hits a certain level like you did for oxygen. As soon as carbon dioxide goes up, you should be breathing faster to breathe out that excess carbon dioxide. That's fundamentally what's going on here. Okay. Now, this is because if your partial pressure of carbon dioxide reaches 90, you are going to go into a coma. If it gets up to 180, you are probably going to die. Okay, so your body is going to respond to carbon dioxide changes really quickly. Okay, so we really need to prevent dramatic changes to carbon dioxide levels, whereas those oxygen levels, we had more wiggle room. So the chemoreceptors are really responsive to carbon dioxide specifically. In fact, our central chemoreceptors, so the ones in your brainstem, right, the ones in your central nervous system, don't respond at all to oxygen, right? The ones in your brainstem will not notice changes to the O2 levels. They do sense changes to the levels of carbon dioxide because that's so dangerous, right? That is the one that we are adapted to sense more. There are some technicalities about how exactly they do that because we have the blood-brain barrier and we're really regulating and controlling what comes in contact with your brain. It happens to be the case that they're not actually responding directly to the carbon dioxide. They're responding to the changes in pH that are caused by changes to carbon dioxide. And that sentence that I just said is the level to which we want to understand this, right? So central chemoreceptors don't respond to oxygen. They do respond to changes in pH, which is an indirect measure of carbon dioxide. So that's it. Okay. All of that is just to tell you, right, that if we were to look at this in graph form, right, if we see our partial pressures of oxygen drop below 60, And normal value, I'll write just on here because I know we just said it, right? Normal arterial PO2 is 100 and pressure of CO2 in those arteries is 40. Okay. So what we're saying is that it takes until we're below 60 before we have chemoreceptors responding. It would just be the peripheral ones. Okay. Rises in carbon dioxide of any type, right? We're not comparing to any value here. Just like as soon as it starts to rise, those peripheral chemoreceptors are responding. Okay. Central chemoreceptors are also responding. There's just a slightly indirect mechanism that involves pH, and you're going to increase breathing in both of these cases. So if you have way, way, way too little oxygen, you're going to want to speed up breathing, okay? Because you're going to want more oxygen. But the most important thing is that if you start to have too much carbon dioxide, you want to immediately speed up breathing so you can breathe off that excess carbon dioxide, because excess carbon dioxide is particularly dangerous. Cool. So those terms from our previous packet, hypoventilation and hyperventilation, are working like this, basically. So hypoventilation, too little breathing. If you're breathing too slow for demand, you'd ultimately want to increase that breathing rate. And the reason for that is largely because you're seeing rises in the partial pressure of carbon dioxide. Hyperventilation, you're seeing really low values of carbon dioxide and potentially high levels of oxygen. You would also detect and respond to this. Okay. So our final concept, which we mainly just like want to know about and get the gist of, is something called the ventilation-perfusion ratio, okay? Which is just referring to the fact that, right, like when we're doing gas exchange, we're thinking about air movement, which is the ventilation portion. But in order to have gas entering the bloodstream and then going around your systemic circulation, you also need to have blood flow to those capillaries that are neighboring the alveoli. So ventilation here, ventilation is movement of air. Perfusion is that movement of blood, essentially, okay? So when we say that we have a ventilation-perfusion ratio, we're saying that we want to match our breathing to our blood flow, essentially. Okay, so we're matching ventilation, which is the movement of air, the breathing, to perfusion, which is that movement of blood to a specific area, okay? So ventilation in this ratio is going to be our rate of airflow. Perfusion is going to be our rate of blood. So V for ventilation, I don't know where the Q comes from, but it's the other one. So Q is the perfusion. So Q is the blood flow, okay? So ideally, we want these to match, right? You want to have the same airflow to match your blood flow when we're looking at that alveolus and that capillary. So ideally, our ventilation, VA, so ventilation to an alveolus, is going to match our perfusion to the blood flow to the capillaries by that alveolus. Okay, so they should match each other. Okay. So here up top, we see that situation. So here we see the rate of airflow coming into the alveolus. And down at the bottom, we see our blood flow Q in the pulmonary capillary next to that alveolus. Okay, so we want them to match each other. And if they do, same rate of ventilation, same rate of blood flow, divide the same number by the same number, you'd get 1. Okay, so that's normal. That's the situation that we usually want. Our issues come if either that alveolus gets blocked or that capillary gets blocked, right? So you can have obstruction of an airway for various disease processes, or say you swallow something or you breathe something in, right? Blocks off an alveolus, or blood flow. Imagine like a clot, something like that. All right, so you can either block airway or you could block blood flow. And either of these situations would change that ratio, right? So if you obstruct that airway, you're going to see a decrease in the ventilation, but nothing's changing about the perfusion because you haven't touched the capillary. If you block that capillary, you're going to see a change in that perfusion value, right? But nothing's going to change with our ventilation value because you didn't do anything to the alveolus. So if we looked at the overall ratio, right, you'd see it drop below 1 if you block the airway because you're dividing a smaller number. You'd see it go up if you have an obstruction of the blood vessel because you have the same number, but now you're dividing it by a smaller number. So you could tell, looking at the ventilation-perfusion ratio, what type of obstruction you have, whether it's in an alveolus or in a capillary. Okay. And you can fix it. Okay. Potentially, depending how complete that blockage is. Okay. So if you have a decrease in ventilation to an alveolus, right? So what we're saying, right, is you obstructed that alveolus, right? So you blocked it off. That's what this first scenario is talking about. Okay. So now you're going to see you can't breathe off that carbon dioxide from that alveolus anymore because it's stuck because there's a blockage. So you're going to see an increase in carbon dioxide. Okay. And you're not breathing in anymore. So you're not getting new oxygen. So you see a decrease in partial pressure of oxygen. Okay. So to try and fix this, you are going to want to adjust your airways and adjust your blood flow, essentially. Okay. So you are going to adjust your airways by responding to that carbon dioxide. So when you see an increase in carbon dioxide, that causes bronchodilation. So bronchodilation. Okay. So broncho referring to the airways, dilation referring to expanding. So if we see a buildup of carbon dioxide in the bronchioles, that means those airways are going to get larger, fatter, decreasing their resistance, hopefully allowing you to move more air more quickly. Okay. We are also going to try to just maintain this ventilation-perfusion ratio. So at the same time as we're doing that, your arterioles, the pulmonary arterioles, are going to respond to that decrease in oxygenation, and they're going to constrict down, meaning their radius is going to get smaller, so their resistance is going to go up. So it's going to slow down the blood flow, right? So we're responding to essentially a slowdown of air, right? Ventilation decreased. So we can try to speed up that ventilation by bronchodilating, but we can also try to slow down the blood with vasoconstriction so that we can match that ventilation-perfusion ratio. Now, the opposite thing kind of happens if you change the perfusion. So if you change the blood flow, okay, so now we're talking about the bottom image. So you obstruct the blood vessel. We're not getting blood flow anymore, okay? We want to maintain that ratio where we have our airflow and our blood flow the same, at ventilation-perfusion ratio of 1, okay? So if we've blocked our blood flow, one thing is we're going to want to try to unblock it, right? So we're going to try to make that blood vessel wider to get around the blockage. So that's this vasodilation piece, right? So we're going to dilate. So we're going to try and make that blood vessel bigger to get more blood. So that's a response to oxygen by the arterioles. And the other thing we can do is try and match it from the airway side, right? So our problem is that we don't have enough perfusion, we don't have enough blood flow, and we're trying to match airflow. So we can try to slow down that airflow to match. So we would bronchoconstrict, make that radius smaller to slow down the airflow in the bronchioles. And that's a response to the partial pressure of carbon dioxide. Okay. So in both of these situations, you can see you rearrange these in your mind a little bit. Okay. So the bronchioles are responding to carbon dioxide. The arterioles are responding to oxygen. Okay. Here we see those. Okay. So again, arterioles responding to oxygen. Our bronchioles mainly responding to carbon dioxide. Okay. And all we're trying to do is keep this ratio of 1. So if our blood flow slowed down, we want to try to speed it up, but also slow down the airflow, because those are the two ways we can make those numbers match. And vice versa. If our airflow slowed down, we want to slow down the blood, but try and increase that airflow. So that's all the ventilation-perfusion ratio means, is that we're trying to match airflow to blood flow. Okay. And we can do that by changing the radius of airways or changing the radius of our arterioles. And in practice, we're doing both of those at the same time. And they're both responses to our partial pressures of gases. Bronchioles mainly responding to carbon dioxide. Our cardiovascular system, our arterioles, mainly responding to the oxygen. Okay. So that is that. So the rest of this is just a flow chart doing that same thing. Don't worry about any of the details in here. You get that fundamental idea of the ventilation perfusion ratio and that we're trying to match these two things. I'm happy.